start painting it again because it takes so long to do it that you got to do it again immediately. And that's the same thing with analyzing the results of your experiment. A lot of times your experiment will teach you things, and that means you need to go back and you need to maybe adjust your goals or refine the model that you're using. It may tell you that your instrumentation needs some tweaking. Maybe it's too coarse or it's too fine or there's a blind spot in your instrumentation. But either way, you adjust and then you go back to the beginning of the process I just described. So now that we've sort of laid out the method, let's actually see how it works in practice. And so what we're going to talk about is the render time in the Firebird app. And this is basically the time it takes from our app starting up until we render ratings and reviews in the page. So first let's talk about the application architecture. It's a statically served single page backbone app. It's hosted on S3 and it's edge cached on Akamai. And the way that our customers, actually integrate with us is that they include in their page a script tag. And that script tag goes to a canonical URL that downloads a thing we call the scout file. And the scout file is a small JavaScript script, and it's cached for a short amount of time. And among other things, what it does is it injects a link for the styles that we're going to use, and it injects a script tag for our actual application JavaScript, which is much, much larger, on the order of 230 kilobytes gzip. And it fetches that from a versioned URL. So when we release a new version of our code, that version changes. And so what we do is we cache that URL, or we tell the browser to cache that URL essentially indefinitely. So it's like 3 years. And the cool thing about this architecture is that it gives us a really nice trade-off between being able to unilaterally push out updates and fixes to our code. At most, the user is going to have to wait 10 minutes to get a new version of the code when we push it out. And it does pretty much the best we can to optimize for the user having a warm cache when they hit our page. When the application JavaScript comes down, then it renders the ratings and reviews in the page. There's also an API request out to our platform that happens, and I'm not going to go into details about that, mostly because it sort of muddies the waters with respect to this model. So let's just ignore it and assume that the data is already there. So what's the problem? This all sounds really great, and in reality it is. The design of Firebird laid like a really good foundation for having a high-performance single-page app. And it does that by having this minimal number of highly cacheable requests. But so we got that in place, and then we started adding features. And the focus was very much on building the app out and adding more and more features to it and providing new functionality to our customers and our users. And performance was not prioritized. And as a result, over time, the render time sort of crept slowly up and slowly up and slowly up. And so when I started at Bizarre Voice in the spring, my lead, Rebecca Murphy, asked me to take a look at this. And so that's what I did, and we're now going to sort of talk about what happened next. So first we set some goals. The median render time at back then was, let's say, around 1 second, which isn't great. A lot of times we were waiting for the API requests, a lot of times we weren't. And so we set the goal of reducing that render time in the near term, the near to moderate term, by 5%, which works out to about 50 milliseconds. And it seems like it should be easy to attain, but it's pretty tough. And in the long term, we set a much, much more aggressive goal, which was to cut our median render time in half. And that's more on the order of a year from now. So we got a goal. Let's talk about a high-level model for Firebird itself. Basically what happens is that there's sort of 5 phases to rendering Firebird. The first part is we wait is the time until the scout file actually runs, is requested by the browser. And that's a thing we don't actually have any control over. And that's something that's going to come up with y'all when you're doing your performance optimization as well, is that there are going to be parts of your model that you won't have any control over. In this case, we don't have any control over it because this process happens when our customer's website injects the script tag into the page. And it might do that in the head, it might do that at the end of the body. In some cases, they wait until the load event fires and then dynamically inject our script. They do whatever they think is the best for their situation, and we offer guidance on what we think is the right move for performance, but at the end of the day, they decide and we can't control it. Once that happens, the browser fetches the scout file. That's another phase. The scout file is downloaded and parsed and compiled and executed by the browser, and it then fetches the rest of the app. And then that's the next phase. And so it takes some time to fetch the application. Basically, we try and pull this thing down from the internet. And then finally, once the app is actually there, it's going to run for a while, do some JavaScripty stuff, and then it's going to eventually take the API data, run it through some templates, and drop a bunch of HTML into the page. And that's the final phase of the render process. So today, what I'm going to sort of really focus on is the fourth step, which is t-app fetch, the time it takes to actually fetch the application. And so this model I just outlined is really high level. It doesn't actually tell you anything about how any of this stuff works. It just lists a bunch of things that happen. So let's make it a little bit more concrete. Specifically, what we're going to talk about, we're going to right now derive a model for fetching a file, fetching the rest of the application over the network. So I think we all have, like, when we first start out, this sort of like intuitive model of how network requests work, right? Like there's like the size of the thing you want, and then there's the size of the pipe that you have that you're going to pull the thing down by, and you basically just divide one by the other, right? Like I want this 100 megabyte file, I have a 5 megabyte per second connection, so it's going to take me, what, that's 20 seconds to download the file. And for large files, this actually is a pretty correct model, but for small files, actually maybe not so much, but we'll get to that in a sec. So here's that model actually instantiated into a mathematical formula. We specify the payload as bytes with the symbol S, and the bandwidth in bytes per second is W, and the time it takes to download a file is the size divided by the bandwidth. This is simple, but it's also like, it's really wrong. Bandwidth measures essentially how fast a sender can put data onto a wire to transmit to somebody else. What it doesn't measure at all is how long it takes that data to move from the sender to the receiver. And that's actually turns out to be a really key value, particularly for smaller files. So our model doesn't account for this, which, and what that thing is called is called propagation delay or latency. And that is the time it takes a message to travel from the sender to the receiver. And there are a couple important things about propagation delay. First, it approaches the speed of light. And in fact, this makes a lot of sense, right? Because a large part of your packet's journey is going to be over some fiber optic backend where it's literally light going down some glass tube. And the more important one from our perspective is that latency is a function of distance between the sender and the receiver. It doesn't have anything to do with how big the file is. And so that means you could be sending a 100 megabyte file or a 10 kilobyte file, and they're going to have the same latency end to end. So let's put latency into our model, and I think this will start to illustrate a little bit better where I'm getting with this. So we add a new variable p, which represents the propagation delay between the client and the server. And so the client is going to have to send a request for a file, and then the server is going to send back a response that is the file. And so we have to pay that propagation delay twice. So we plug that into our model. We have t equals 2 times p plus s divided by w. And let's actually work this out as a real quick example. Let's talk about, we're going to have a 40 kilobyte file for bandwidth, 21.2 megabyte or megabits, excuse me, per second, which works out to about 2.5 million bytes per second, and a latency of 17.5 milliseconds. I pulled these from, there's an FCC government report. I'll link to it in the slides. And so what you end up coming up with is that it's going to take 50 milliseconds to pull this file down, according to our model. And one thing that's important to note is that second to last line, on the left-hand side, that's 35 milliseconds just of latency. So fully 70% of the time it takes to download this file is latency. It doesn't have anything to do with the bandwidth. You can make the bandwidth infinitely fast, and it's still going to take at least 35 milliseconds. But it's worse, right? Because we're not actually just like sending these files back and forth. We have to, like, we're making an HTTP request, and HTTP goes over TCP. So what is TCP? TCP is a core network protocol. Its inventors, Paul Irish and Alex Sexton, claim that, like NPM, it doesn't actually stand for anything, but we actually know that it stands for taking care of packets. TCP provides like a reliable connection, which means that what the actual upshot of that is that every single packet has to be acknowledged. And it offers a connection-oriented delivery of these packets. And what that means is that you have to set up a connection from your client to your server. If you're going to send TCP between any 2 points on the internet, those 2 points on the internet actually have to set up a connection between each other and maintain that connection. And that connection requires some overhead, which I'll talk about in a sec. Specifically, the process of initiating connection takes a round trip to the server. So we have to send a message to the server has to respond with another message, and now we have a connection. So this thing is starting to get a little bit complicated. We're seeing a lot more of these round trips, and so let's just refer to those by what most people call them, which is called round trips. And that time is referred to as the round trip time, or RTT, which is just 2 times P. Okay, so now we have a new model. We're going to need 2 RTTs to get this data, right? We got 1 round trip to set up our TCP connection. And then we have another round trip to actually make the HTTP request and fetch it back to the browser. So this adds another 35 milliseconds to the time that it's going to take to fetch this stuff, right? We've added one round trip. A round trip is 35 milliseconds. So now 82% of the time that it takes to fetch this file is due to propagation delay. But it gets worse. So the other thing that TCP does is it deals with congestion in the network. And it does this in 2 ways. The one that most people are familiar with is called congestion control, which is that TCP detects that there's congestion in the network basically by, if it doesn't get an acknowledgement of a packet, then it assumes that that packet was dropped due to congestion, and it cuts how fast it's sending data in half. And it sort of keeps track of this thing called a window. And that cutting it in half is called an exponential backoff. But that's not what I'm going to talk about. What I'm going to talk about is the other thing, the lesser known thing, which is congestion avoidance. And that is that during the very beginning of a TCP connection, the sender maintains a different window, private, unadvertised window. And it artificially limits how much data it will send until it starts getting acknowledgments back from the distant end. This thing is called a congestion window, or C-wind, and it's typically 4 to 10 packets. And so that works out to about 15 kilobytes on most computers. And what happens is for each so you send, if you have a long enough latency in the pipeline, then the sender will transmit 10 packets, and then it'll wait for acknowledgments to come back. And each time it gets an acknowledgement, it'll increase its C-wind by 2. And the upshot of this is that essentially every RTT, you're going to double your C-wind. So what does this mean? Like, why am I telling you about all this? Here's what I'm trying to tell you, which is that during your first RTT, your bandwidth is artificially constrained. Like, you could have a gigabit connection, but during the first RTT, you're only going to get 3.4 megabits per second. And the way that I come to this number is you're sending 15 kilobytes, and you're waiting, that's the most you will send during that first RTT, and RTT in this case is 35 milliseconds. You divide that out, you get 3.4 megabits per second, which is about 16% of the available bandwidth for my example. For large files, for long connections, this doesn't matter, right? Like, this is just the first few milliseconds of request, and who cares? But for web apps, we care because almost everything that we do is during the early part of a connection. We're requesting a bunch of small files, or maybe only a few slightly larger files. But either way, we're not going to be doing a whole bunch of round trips to the server. And so slow start can have a real effect on on how long it takes us to download our stuff. So let's refine our model even further. So if we add in the idea of this C-wind or congestion window, and we define that in bytes as C, then we can find the number of round trips to download a particular payload of size S using this formula. And I don't want to go into where that formula came from. I asked a buddy of mine who's a math PhD to help me figure it out. And so that tells us the number of round trips it'll take to download a particular payload of some size. And now we update our model to say, okay, it's now going to take us the RTT, so how long it takes a round trip to occur, times 1 round trip for the connection setup, plus R round trips to download the payload, plus you still have to pay for the time it takes the server on the other end to actually put data on the wire. So let's take a look at our example again. Let's set C to 15 kilobytes, which is fairly normal. And if we do this, then we can figure out that it's going to take 2 round trips to fetch our payload instead of the 1 that we were thinking it was going to take us. And if we put all that back into our model, we're going to end up with 120 milliseconds to fetch a 40 kilobyte file. And 87.5% of that time is because of latency. So now imagine that your latency is higher, that you're over, say, a mobile connection. Right? This is why latency is so critical to web performance. And really, you don't actually have to pay much attention to bandwidth at all. So again, let's talk about how realistic this model is. It's not, it's more realistic than our original model, but there's still all sorts of things going on. The internet is like really super complicated, it turns out. And there's like lots of proxies and routers and all sorts of things going on. And they're all playing games. They're all trying to optimize this thing in different ways. And sometimes the way these things interact can be kind of counterintuitive. But for our purposes, it's good enough. It doesn't matter. It approximates the reality that we're trying to understand. And we're going to use it in a sec to actually make predictions about what happens when we vary some of these variables. So let's briefly talk about instrumentation. Instrumenting network requests is kind of tough in the browser because, particularly as a third-party app, JavaScript doesn't have a whole lot of access to timing data about requests for resources other than the page itself, right? You've got the navigation timing API, and that'll tell you things about how long it took to like do the DNS resolution for the page and to fetch it down and all that sort of stuff. But that's not helpful for Firebird at all. We don't care about that. What we care about is how long it takes to fetch our resources, and that's not exposed in a cross-browser manner. There is a new API called the Resource Timing API. It's available in some of the browsers, specifically Chrome, IE, and Opera, I believe. I think in Firefox it's behind a flag. And that'll actually give you that data for resources. There's some like cross-origin stuff that you have to like send a header down. But unfortunately, it's not available across all these browsers. And so what you end up doing instead is you know when you fetched your resource. So you start timing then, and then if it's a script, then at the very beginning of that script, then you mark the other end of your time and you say, all right, that's how long it took to fetch my JavaScript. It's really not, right? Because what actually happened was not only was a network request made, but then the browser had to parse, compile, and start executing your JavaScript. But it turns out that in most cases, that last bit is not a huge contributor to the time it takes. And you don't really have a better choice, so you just gotta kind of take it. So let's go back to how Firebird works. And if you remember, I said that what the Scout file does, once it starts running, is it injects a style link tag and a JavaScript script tag that point to the app styles and the app script, respectively. It turns out that what we were doing is we were, what seemed totally reasonable, which is we were putting the CSS in first, and then we were putting in the JavaScript. And so I said my one-weird trick was going to be the like rigorous approach. This is actually the one-weird trick. It turns out the browsers reuse TCP connections because they know that it actually takes some time to set these things up. And so if you request a file, the Scout file in particular, from some domain, when you make your next request, that request is going to go out over the existing TCP connection. And the reason that's important is because Slow Start has already had one round, right? So we've already increased our C-wind. We have a higher C-wind starting out for this next request. So the question that I asked was, okay, well, does it matter whether we request the JavaScript first or the CSS first? Like, is this going to make a difference? So let's ask our model. We're going to start with the following. These are the values that I used when I actually did this experiment. They're different than the example, but it doesn't really matter that much. So an initial C-wind or congestion window of 14.6 kilobytes. Our bandwidth is going to be 5 megabits per second, or about 625 kilobytes per second. And our round trip time is going to be 42 milliseconds. So in the status quo, we plug all this stuff in. We expect that the CSS is going to get that existing connection, and it's going to have an approximately 30 kilobyte congestion window when things start out. It's going to have a higher C. while the JavaScript is going to get a whole new connection, right? Like we're putting these two things in. The browser had one existing connection to our server, and now it needs to open another one. And so our model predicts that the CSS is going to take 156 milliseconds to fetch, and the JavaScript is going to take 617 milliseconds to fetch, which is quite a while. You start to see where the 1 second render time is coming from. Well, let's swap these. What does the model say if we swap the order of these two things? Well, then the CSS is going to get the smaller C-wind, and it's going to have to pay to set up a new connection for itself. So it's going to take longer. In fact, it's going to take almost 200 milliseconds, 198. But the JavaScript is going to get the already open connection with the already larger C-wind. And so it's going to take less time, 533 milliseconds, to fetch this stuff. So the end result is that we expect the CSS to take 25% longer and the JavaScript to take 14% less time.